What we had obtained in this way is, you see, classically counting the number of microstates doesn't make any sense because the position can have continuous values, the momentum can have continuous values, and all different values correspond to a state, a different state, classically speaking. And in a sense, every point in our phase space on this hypersurface determined by the energy gives us a new microstate, but there are infinitely many points on a surface. So classically, this identification of number of states is kind of problematic. There's no such problem in quantum mechanics, but we kind of borrowed the idea from quantum mechanics, and we said that, okay, in phase space, we cannot really localize any microstate to a single point. Every microstate will have some finite volume. And hence, if we know the volume in phase space, then dividing by this total volume by the volume occupied by each one of the microstates, we can identify the number of microstates even classically. So that is why we had introduced this constant omega 0 in our phase space volume. But quantum mechanics already tells us that that volume should be 1 over 2 pi h bar for each momentum and coordinate pair. Well, which from the Heisenberg uncertainty principle also makes sense, because the Heisenberg principle tells us that the uncertainty in the position and the momentum, if we multiply them, it should be something of the order of h bar at least. H or h bar. Well, of course, it doesn't really tell us what the exact coefficient is, but this explicit derivation tells us that that coefficient has to be equal to h. So for each momentum coordinate pair, we have a factor of 1 over h in our phase space integral.
John, what was the reason that it is twice the uncertainty limit?
This one.
Not h over 2.
Here. Well, that is why I put the somewhat of the order of h.
Yeah. Okay.
The exact number could have been h over 10 or 10h. We cannot really say. The only thing I can say is it should be somehow of the order determined by h itself. And the treatment starting from the discrete states in quantum mechanics allowed me to determine that value to be exactly h. And now we started looking at the concept of the ensemble. So basically what we are looking at is, just imagine our system. It is just evolving in time. It's constant. Its microstate is constantly changing, but the macrostate is constant. So rather than looking at a single one of them, we just make many copies of this. Almost infinitely many copies of the same system. Of course, each one of these will be in a different microstate. So averaging over the microstates of a single system, or averaging over the microstates that my single system will pass through during my measurement, would be more or less the same thing as averaging over my ensemble. But if I have many copies, each copy will be a point in my phase space. So if you just imagine in phase space, I have all these points which are evolving in time, meaning the position of the particles will be changing, the momentum will be changing. It basically means that each one of these points corresponding to the copies in my ensemble will be changing in time. But still, if I have many of them, they will be almost continuous in phase space. So I can talk about the density in phase space of these ensemble copies. And averaging over time or averaging over ensemble will be basically averaging over this density.
Does the ergodicity principle enables us to use ensembling?
No. Up to this point, I didn't make use of ergodicity. I'm just saying that I have infinitely many copies of the same system. And then each one will be in a different microstate. Each one will correspond to a point in phase space. So if I have many of them, they will look almost continuous. I can even define a continuous density in phase space. In some places, this density might be 0. In some other places, it might not be 0.
How can we be sure that if we follow a single system to determine infinity, how can we know suppose a particle moves around all possible states?
I don't know. I didn't make such an assumption. I'm just saying that I have this system, or I make many identical copies of the same system. They will be at different times in their evolution, at different points in the trajectory of one system. That's all I've made up to this point. I mean, it might be that my system doesn't reach some of the allowed phase space, in the sense that it might be trapped in some kind of a local minimum, which doesn't allow it to go to the other points which are allowed only by the macro state of the system. Fine, that will only tell me that rho is non-zero in some regions of the allowed phase space. But since I didn't make any assumption about rho yet, I'm not using the ergodicity yet. I will be using in the next step. So any questions up to here? We will come to that in a moment. Other questions in this derivation? Other points you want me to repeat? Okay, so now what I would like to do is study the properties of this rho. You see, rho will be a function of all the coordinates and momenta of my system. Well, depending on the system, it might even have some external time dependence. For example, it might have an external potential acting on my system. You see, up to this point, I'm not even assuming that the system is in equilibrium. I'm just making many copies of my system. Each one of these copies will be shown by some point in phase space. And so there will be some density in my phase space. And in my phase space, all these points will be moving around. So I can ask the question, how does this rho change with time? So I can look at, let's say, d rho by dt. You see, this is also pay attention to total time derivatives and partial time derivative. This is a total time derivative, meaning that I'm picking a time, I'm picking some time, some point, and I'm moving with that point along its trajectory. Because I will assume that Qi and Pi, they will also be evolving with time, this T over here. This will be equal to, well, the derivative of rho with respect to Qi dot, derivative of rho with respect to Pi dot, and plus the explicit time dependence. If any. And I'm not writing it explicitly, but there is always a summation over I from 1 to n, or if you like 3n. I'm summing over all the components of the position and momentum of all the n particles.
We switch back to the three-dimensional.
No, this is not three-dimensional. This is an arbitrary dimensional. Which is equal to, well, let's remember the Hamilton's equations of motion. Qi dot is, do you remember? From classical mechanics or analytical mechanics. Del H by del Pi, my system has Hamiltonian, and Pi dot will be minus del H by del Qi. So if you come back over here, this is I from 1 to 3, and well, let me ignore that. I will not be writing it explicitly, it's always there. This will be del rho by del Qi, del H by del Pi, minus del rho by del pi del h by del qi plus del rho by del t. Does that remind you of anything? It's the Poisson bracket. So that is the Poisson bracket of h and rho with respect to pq plus del rho by delta. Yes, again, up to this point, I'm not really making any assumptions. I'm saying that I have many copies of my system at different times in their evolution. I just put them in, consider them in phase space, consider all the points in phase space. If there are, I have sufficiently many points, I can almost treat that points as a continuum distribution. And they will evolve. So I can define the density will evolve, and the evolution of the density should satisfy this condition. So the total number of points I have in phase space, how does it change? It doesn't change. I have the copies, the number of copies is constant, so the total number of points in phase space does not change. Do you agree with that? So if I started with, let's say, 10 copies of my system, that means I have 10 points in my phase space, and as my systems evolve, all these 10 points will be moving around, but I will always have 10 points. Not any more, not any less. Even quantum mechanically. Even if I treat the system quantum mechanically, you see, if I have 5 copies of these board erasers, 3 copies, as they evolve in time, I will still keep having 3 copies of these whiteboard erasers. But that means that this total time derivative should be 0. As I move with the flow, if I have, let's say, 5 copies in my vicinity, well, I should still have 5 copies in my vicinity. I'm moving with the flow. New points are not appearing, and the existing points are not disappearing. Again, up to this point, there are no assumptions. The system doesn't even need to be in equilibrium. I can consider a single oscillator as my system, then have 5 copies of this oscillator. This will still hold. Now I'm making assumptions. I will assume that my system is in equilibrium. Which means that when I look at the system, when I look at my phase space, things shouldn't be changing with time. Let's say if this is my phase space, I just look at this point and keep looking at this point. There will be new points entering that region. Existing points will be leaving that region. But if my system is in equilibrium, if all my systems are in equilibrium, there shouldn't be accumulation of points in a given region or a depletion of points from a given region. So if I am in equilibrium, when I look at a particular point and study it over some time, it shouldn't change. But that basically means that del rho by del t, there shouldn't be any explicit time dependence. Now I made the assumption of equilibrium. Well, which tells me that h rho, the Poisson bracket of h and rho, should be 0. We will also do this derivation in for a quantum mechanical system. In that case, we will have the commutator of h and rho. They have to be 0. Basically, rho commutes with the Hamiltonian, rho is conserved, something that is conserved. Now let me make, well, any questions up to here? Let me make an alternative derivation of the same result. So here what I used was, okay, still I will use this condition. Is this condition clear to you? The total time derivative should be 0. Why is it 0? I said that the conservation of the number of copies makes sure that that is 0, but why?
Case of equilibrium.
No, that is always valid. That is not an equilibrium condition. Partial derivative should be 0 in equilibrium. That is my equilibrium condition. The total derivative has to be equal. Whether my system is in equilibrium or not, it doesn't change. Let's do an alternative derivation. I have my phase space, this multidimensional space. Let me just look at some region in my phase space, some arbitrary region. Yes. You can choose whatever is your favorite shape. Just take that region. There are some number of points inside that region. This might be changing. So the change in the number of points inside my region, well, there can be various reasons for that change. For example, points might disappear or just appear. That might be one of the reasons why the number of points inside that given region might change. But that would be the case in systems where the number of points is not conserved. If the number of total points is conserved, in that case, if the number of points inside the region changes, it basically means that they either moved out of the surface of the region or they moved in from the outside. So this should be equal to minus the total flux. So this is the change in the number of points in the region per time will be the total flux through the surface. Of the region. So if there's a conservation law, this should be satisfied. And since by construction I'm just making copies, I'm just letting each copy to evolve, well, the number of copies is fixed. The point representing the copies of my system, they will be just moving around in my phase space. I'm not adding new copies, I'm not removing copies, so the number of points in phase space is conserved.
So we have corresponding current?
Yeah, there should be a current. Well, what's the number of points inside my region? Let me say dv small v rho will depend on Q, P, and T. Now keep in mind that V is this many-dimensional volume element in my phase space. Q is all the position coordinates, P is all the momentum coordinates. So this is the integral over the region. This should be equal to minus over the surface of the region of the current. This is the boundary of the region. So you see, whenever you have a conserved quantity, and whenever you can talk about the density of that conserved quantity, there will always be some current corresponding to that density, and whatever that conserved quantity is, it should satisfy this equation. The integral of the density over a volume, if you take its time derivative, that will give you the rate of change of the total quantity within that region. If that quantity is changing, it has to be due to some current passing through the boundary. So that's what we mean by conservation. And this J will be essentially the density. The current is always the density times the volume. Sorry, density times the velocity. What is this velocity? But again, I repeat, R is the position in this multidimensional space with coordinates Qi and Pi. So this is my velocity in this multidimensional phase space. Well, let's go back to this continuity. Well, this is nothing but the total time derivative. This should be equal to minus ds times j. Well, if I move the time derivative, you see, p and q are dummy variables. I'm integrating over them. They are not time dependent in that sense. The only time dependence of that integral is due to the explicit time dependence of rho. So that integral is actually partial derivative of rho with respect to t. This should be equal to minus. Now I can use the divergence theorem. If I'm integrating a vector current over a surface, it should be the same as the integration over the volume of the divergence of that current over my region. But this tells me that over the same region, that integral should be 0. But my region is arbitrary. If my rho corresponds to a density of a conserved quantity, whatever the region I choose, this integral should always be 0. And the only way it will be is if the rho by dt plus divergence of j is equal to 0. Now, the divergence of a vector is basically, I remember j is qi dot, pi dot. This is my j.
Times rho.
No, sorry, this is my v. This is my v. J is rho times v. R was qi pi. Divergence of any vector is just take some component of that vector, take the derivative with respect to that component, and sum over all the components. Well, J has components corresponding to qi. I take the derivative with respect to qi. And it also has components with p corresponding to pi, I take the derivative with respect to pi. This should be equal to 0. Well, let me take the derivatives. d rho by dt plus d rho by del qi dot plus del rho by del pi dot. This is what I already had before, remember. Here. Del rho over del qi dot plus del rho over del pi dot. That part and this partial derivative I already had. This is 0. I have some extra terms. Now, what are they? I have rho del qi dot by del qi plus del pi dot by del pi. Should be 0. Now, let's see what that parenthesis is. Remember, qi dot is nothing but del h by del pi. So if I take its derivative with respect to qi, it is the second derivative. Well, second derivatives, I can change their orders. Well, del h over del qi, again, I can use Hamilton's equations, is nothing but minus pi dot. So as long as I have a Hamiltonian, this will always be 0. So I'm left with my earlier equation, which basically implies that del rho by del t is equal to 0. Okay, we are basically doing more or less the same thing. If the quantity is conserved, if I move with the flow, the number of points around me shouldn't change. If it is conserved. That is what I used before in order to write this down. Just say it. Now I have an alternative derivation of more the same quantity, but where I started is if it is conserved, if the conserved total quantity within some volume changes, it has to be through the current running through the surface. And I obtain basically exactly the same result. Both of them just tells me that the quantity is conserved. Are there any questions up to here? This is called the Liouville theorem. Rho is conserved. In equilibrium, rho commutes with the Hamiltonian. Okay, let's look at one more property of this rho, of this density. Let's say that I have two systems in equilibrium with each other. One will have its own phase space with the density rho 1. The other one will have its own phase space with a density rho 2. But now I can also consider the whole system and look at the density of the whole system. not just the first system or the other system, but the whole, all of it. How are they related? Row 1 and row 2. Well, let's look at this microcanonical the ensemble picture point of view. You see, this is my first system. Let's say I have an ensemble of that one. I have an ensemble of the other one. So if I just combine them, basically for each copy in the first ensemble, I can take any one of the remaining ensemble. So in this combined ensemble, let's say, the number of copies I have would basically be the product of the copies I have in each one of those ensembles.
Could you repeat?
You see, let's say that for the first system, I have N1 copies in the ensemble. For the second system, I have N2 copies. If I am constructing the combined system, well, the combined system can be this and this, this and this, this and this, this and this. All the pairings. So the combined system has N1 times N2 copies. Should have N1 times N2 copies. What else I know? Let's say that I'm calculating some property of the Q1 system. This average. Well, on one hand, this should be dQ1, dP1, row 1 of F. Let me call this F1. But on the other hand, I should also be able to get the same average from the combined system. I'm just making a measurement of the first system. I can either treat it isolated, or I can treat it as a part of the combined larger system. Since my system is in equilibrium, my system will not change whether I treat it isolated or a part of the larger system. Nothing should change. So this should hold. At the same time, if I calculate the average of some quantity of the second system only, I should have the same property. I can integrate over the phase space of the second system only of the density in the phase space of the second system of whatever that function is. Or I can just look at the whole system and integrate over the phase space of the whole system. Well, what this basically tells me is that if I take this row of the combined system, if I integrate over the momentum and coordinate of the first system, I should get the density in phase space of the second system. And, well, if I integrate over the momentum and coordinates of the second system, of the combined system, I should get the density in phase space of the first system. Also keep this in mind. Yeah, what all of this tells me is that the rho of the combined system is nothing but the product of the density in phase space of the first system times rho of the second system. Or let me just remove the arguments. Rho is equal to rho 1 times rho 2. Or logarithm of rho is equal to logarithm of rho 1 plus logarithm of rho 2. So what do I know? I know that rho is conserved. So logarithm of rho is also conserved. Furthermore, logarithm of rho is not just conserved, it's an additive conserved quantity of my system. Because if I divide my system into two, logarithm of rho of the combined system is the logarithm of rho of the first system plus the logarithm of rho of the second system. I don't have so many combined additive conserved quantities. In general, I only have energy, number of particles, angular momentum, linear momentum. Unless there is some other property of my system, these are the only conserved quantities in my system. Only additive conserved quantities. Which basically tells me that logarithm of rho should be a function of, it can be a constant, or it can be some function of the energy of the system, or it can be a function of the number of particles of my system, or some function of linear momentum, some function of the angular momentum. These are the only additive constants that we know from classical mechanics for a general system. Well, I can always go to a reference frame in which P is constant, P is 0. I can always go to a reference frame in which L is 0. So by just changing my reference frames, so logarithm of rho should be some constant minus beta E plus mu beta N.
How are you deciding the plus and minus signs?
Well, at the moment, this A0, beta, and mu, they are just arbitrary numbers. I don't know what they are. You can just choose whichever plus or minus sign you like. Why did I write mu times beta rather than just mu? Well, you can also do that also. There are just some constants multiplying N and E for the time being. Of course, we will relate them to some physical quantities eventually, but for the time being, just treat them as constants. Well, in the microcanonical ensemble, you see, when I was looking at this ensemble theory, I had many copies of my system, identical copies, and they were evolving in time under some influence. I didn't say that there is no external influence. They can be also have external influences. The system need not be isolated. But the results I obtained that rho commutes with the Hamiltonian is still valid. Now I'm only considering isolated systems. That is what we have in the so-called microcanonical ensemble. But if it is isolated, E and N, they are both constant. I don't allow them to change. But if they are all constant, A0 is constant, beta and mu, they are constant. Now E and N, they are also the constant. So logarithm of rho is constant. So what is the rho of, let's say, at the point PQ in phase space? Well, first of all, it is 0 if PQ corresponds to a microstate with a different energy than the energy my system has, and constant otherwise. Now I will be using the ergodic hypothesis. I will say that if I wait long enough, my system will get arbitrarily close to any point in the allowed phase space. This is my assumption. This is the so-called the ergodic hypothesis. Well, it does work for almost all the relevant systems. Of course, you can come up with systems in which this will not work, but for a realistic application, for a realistic system, it seems to hold.
Hocam, is this equivalent to if you wait long enough, the system will pass through all of the microstates?
Arbitrarily close to all of the microstates, let's say. I'm not so sure whether you can actually point that it will pass through all the points. You see, trajectory is a line. If it passes through all the points, a line should be filling this area. There are pathological examples that does that, but in general, this line will not do that. It will be a smooth line. So it will not pass through all the points, but it will be very dense. It will pass through arbitrarily close to any point. Well, remember we had already defined some quantity. Rho is the number of allowed states in phase space. So, number of states in the allowed phase space. And remember, rho, if we sum over or integrate over, whichever one you prefer, over all states in the allowed phase space, this should be 1. This is how we define this density. We defined it to be normalized to 1. But this basically tells me that rho is nothing but 1 over omega. And if you like, you can also add so on this surface, it has a constant value of 1 over omega. Outside this allowed surface, it is 0. This is our density in phase space. Now let us go back to our definition of the entropy. Remember, entropy, we had defined it as logarithm of omega. Well, let me write it slightly differently. This is logarithm minus logarithm of 1 over omega. So 1 over omega will be my rho, essentially. Well, this will be equal to minus sum over all allowed microstates of logarithm of 1 over omega times 1 over omega. You see, for all the microstates, omega is constant. So if I sum over all microstates of logarithm of 1 over omega, it's just logarithm of 1 over omega times omega. So I'm just dividing by omega. So these are basically the same thing. But this is nothing but minus the expectation value of logarithm of rho.
There is a minus in front of it.
Yes, there's a minus sign. Well, you see, rho is, since it's positive, its integral is 1. Rho is, in fact, kind of a probability. If you pick an arbitrary copy in this microstate, that gives me the probability that it will be within that region. And, sorry, logarithm of rho is a negative number, so minus the logarithm of rho is a positive number, so that expectation is a positive number. Entropy is a positive number, yes.
I don't see the second step. Can you expand a bit maybe?
Okay. So let me ask you this question. What is the sum over microstates of 1? What is this? This is just omega. If for each microstate you assign 1, you sum over all these ones, well, that gives you the number of microstates. Or sum over microstates of 1 over omega is also 1. Well, sum over microstates of 1 over omega, which is 1. I can multiply this with logarithm of 1 over omega. Well, this is nothing but logarithm of 1 over omega. But since this is a constant, I can move it inside that summation. Which was minus the entropy. Now 1 over omega is rho. So this is, I basically recover this expression over here. I'm back there. And in fact, this turns out to be this definition of entropy. Logarithm of the probabilities turns out to be more generally applicable. We also canonical ensemble and the grand canonical ensemble, in all cases, this is valid. In fact, this is called the Shannon's entropy from information theory. Any questions?
You fix the n, right? Number is fixed.
Which n? The number of copies?
You were told me about microcanonical.
Yes, n is fixed.
Yeah.
In fact, you see, since we are looking at the microcanonical ensemble, logarithm of rho in general has this expression. E is fixed, n is fixed in the microcanonical ensemble. For example, we will look at canonical ensemble where n is fixed. So rho is just e to power minus beta e, proportional to that. A0 is the normalization constant. And now we will look at the grand canonical ensemble, and beta will turn out to be 1 over temperature. In the grand canonical ensemble, we will allow n to be also variable. So the logarithm of rho will have all these three terms. and mu will turn out to be the chemical potential. In fact, since I know the answer, I know their physical interpretation. That's why I chose those sign conventions, and n is multiplied by mu times beta rather than just a single constant. But I could have just called them some arbitrary different letters and then change their definition later on. Any questions? So let's give a break now. Just move around a bit, wake up, have a coffee, and see you in 10 minutes.